All right, this is going to be a short video in terms of the number of slides and things that we do. We're going to talk about logarithmic differentiation. The summary here of what we're going to talk about is maybe a little heavy-handed, but I find that students come into college-level math classes with this idea that logarithms are bad, that they are hard to work with, that they're weird. Folks, it's time to get comfortable with these things. Properties of logs are really good. The whole point here is that we're going to stop the logarithm hate, stop the slander. Seriously, logs are awesome. That's what we're going to be doing here. So, okay, why are logs nice? What are the properties of logarithms that make things helpful or that make them helpful? Well, they really just do these nice things to operations, to products, to quotients, to exponents, things like that. So let's see what we've got. We've got three basic properties of logs that we're going to take advantage of right now. The first is this product to sum property, meaning if we have some sort of a product inside of a logarithm, and we could change this natural log to maybe any log. I'll do log base b, although we're going to pretty much do natural logs. We can split this up into a sum of logarithms. So they turn a product of things into a sum of separate logarithms. And we saw this in the last example of the last video, right? That was a really helpful thing. Similarly, with quotients, they turn those things into differences. And then lastly, they take exponents and turn them into coefficients. Now we're going to use all natural logs for these because they're going to be nice to work with, but these properties are really nice. These will be really helpful for us to do. So what we're going to have is, oops, I meant to highlight this, not erase it. What we're going to have is some big product or quotient or things with exponents on them, and they're going to be hard to work with. We're going to apply a logarithm in order to take advantage of these properties of logs. So we're going to do the seemingly wild thing of pulling a logarithm out of a hat and introducing it to make things that are hard look easy. Again, that seems to be counterintuitive for some students at the beginning of this because they're used to this mentality of logarithms are hard, logarithms are bad. We need to scrub that from our mind. Logarithms are our friends here. They're going to be really, really helpful. So here's the general idea. We're going to have some function that's going to be really, really weird. It's going to be difficult. We're not going to know how to differentiate it. We can write it as just an equation, y equals whatever that function is. And then if we apply a log to both sides, we'll use properties of logs to help clean up the right side of that equation, and then we can use implicit differentiation to find y prime. This is going to be a pretty great little process for us. So let's take a look at some of my favorite examples here. This is a really classic logarithmic differentiation example. This function is called the tower function, or sometimes people will call it a hyperexponential function. It's not an exponential function because it's not a base raised to an exponent, because when we think about this base raised to an exponent, that base is just a fixed number. And here, our base is variable. And it's not a power function because it's not x variable raised to some fixed number exponent. It's kind of like halfway in between, right? So how do we differentiate this? Well, what we're going to do is say y equals x to the x, and then we're going to go ahead and tack a log onto everything. So we're going to say the natural log of y equals the natural log of x to the x. So we're going to introduce this log. Notice we can use a log property here. Let's pull that x out front. So what we really have is the natural log of y equals x natural log x. And now if we want to find a derivative, we can just go ahead and say the derivative of natural log y will equal the derivative of x natural log x. We have some chain rule on the left, and we have a product rule on the right. But notice that these chain and product rules are using just basic function types. So the derivative of the natural log of y is going to be the derivative with regard to y of the natural log of y times the derivative of y with regard to x. Or you can say it's y prime times 1 over y. Oops. I need to clean up this with my eraser, but I can't find my eraser button. There we go. And then over here, we're going to have a product rule. That's going to be the derivative of x times the natural log of x, plus x times the derivative of the natural log of x. So we've got y prime equals y times natural log x plus 1. So this is a little weird because the derivative here is written in terms of x and y. But wait a second. We know what y is. So let's just go ahead and put that in. So y prime is x to the x, natural log x plus 1. There it is. That's the derivative of this hyper-exponential function or tower function. Logarithmic differentiation gets us there. And what you'll notice is that once we have this set up, there's nothing different about what we're doing here. We're using implicit differentiation, and we're learning these new, or we have learned, these new derivatives of the natural log function. That's all we're really using here. All right, let's do this again. This one's a little bit harder. Not really. If y is equal to 1 plus x squared raised to the natural log x, then let's apply our logarithm. And we've got the natural log of y is equal to the natural log of 1 plus x squared raised to the natural log x. And we're going to do the exact same thing that we did earlier. That exponent comes out front. So let's do it. Let's grab this natural log of x and pull it out front. And let's notice the kind of structure that we have. We're going to differentiate this. We're still going to have some chain rule over here. And we're still going to have some product rule over here. Now notice this part is chain rule too. So when we start differentiating this, we'll just keep all that stuff in mind. The derivative of this left side, though, is not going to be a big deal because we've already done it. You're going to get used to doing that derivative quite a bit. The derivative of the natural log function for some other variable. So we've got y prime over y again. And now over here we can say if u is the natural log of x and v is the natural log of 1 plus x squared, then u prime is 1 over x, and v prime, this is a little tricky. We're going to think of this just like the left side of our equation here. It's going to be the derivative of 1 plus x squared over 1 plus x squared. So 2x over 1 plus x squared. All right, so now we can just do our product rule. We've got the natural log of 1 plus x squared over x plus 2x natural log of x over 1 plus x squared. I'll multiply everything by y. And there's some ways that you can rewrite this, right? We could find common denominators and combine these fractions and all that stuff. But I might just leave this. Y, I know, again, is 1 plus x squared raised to the natural log x. Doesn't this look terrible? Look at all this stuff that we've just found. But notice that we can find it, I don't want to say easily, but through a pretty nice little process. This idea of logarithmic differentiation gives us the ability to find this weird-looking derivative through implicit differentiation after applying logarithms. All right, give this one a shot on your own. This one looks big, right? But write everything with some exponents. So maybe convert that square root, right, to something like x minus 10 raised to the half. Throw some logs on this thing and see what happens. See if we can split this thing apart into some smaller pieces that we'll be able to differentiate nicely. All right, hopefully this is where you're at. Take a look at what we've done here. We've got all this product and division that I split up into sums and differences of logs. And then I also just used a bunch of exponent properties to pull exponents out front of logarithms. Technically on this one, there's a little natural log of e. But again, the natural log of e is just 1, so I got rid of that. And now I'm just applying the derivative to everything. Y prime over y is equal to, you ready for this? This is going to go fast. 3 over x plus 4 plus 2x minus 15 over x minus 1 over x minus 10. And so if we want the actual derivative here, y prime is going to be equal to y. I'm just going to write that big fraction y. I'm not going to write the whole thing because I'm lazy. Times this sum, 3 over x plus 4 plus 2x minus 15 over x minus 1 over x minus 10. Oh, I forgot my half. Sorry. I was saying that looks a little weird. There we are. So this is 1 over 2x minus 10. So maybe we'll just call it 2x minus 20. There we go. You could take this big, ugly fraction and shove it in there, and that's what this derivative rule really is. Logarithmic differentiation helps us with this, gets us through this problem. It's not a nice looking answer, but at least it's attainable, right? It's something that we can get to. And I'll tell you what, it sure beats the pants off of trying to do the quotient rule on here with a product rule in the numerator and in the denominator and chain rule along the way. Doesn't that sound terrible? If you don't believe me, just try it. Hopefully you'll notice that this logarithmic differentiation process is really nice for an example like this. Okay, so summary. I can't stress this enough. Logs are nice. We like logarithms. Specifically, when are they nice? For big products. That's not how you spell products. I'm missing a letter. Products. For big quotients. Or for some function raised to another function, like that hyper-exponential function or the tower function that we looked at, because the properties of logs do a really good job of cleaning these things up. That's specifically why logs are nice. Okay, from here, we are almost finished with learning derivatives of functions. We have inverse trig functions left, and along the way, we'll talk a little bit more about inverse functions in general. We've defined a process now through this work with logarithms earlier, and exponentials, finding those with implicit differentiation. We've developed that process. We're going to use that for these inverse trig functions and inverse functions in general, and we'll see how things go.